Okay, well, it's recording anyway. It'll probably fill up, and then there'll be like a big problem. We don't know what happened. Okay. So the derivative of this expression, we have two parts, and we have a j. So really, there's three things here. Now, you know from calculus that there's going to be multiple things to consider, right? We got derivative. You got to do derivative. What is it called? When there's there. These are. Dang, I forgot the name of the thing. Anyway, so d dot theta dot j plus d theta double dot j plus, how is the j changing? So we took the derivative of the d, we took the derivative of the theta double dot. Now, just product rule, that's right. Then now we got to take the derivative of the j itself. So d theta dot j dot. What's j dot? J dot is equal to theta dot k cross j, which is theta dot I, actually negative theta dot I. So if you look here in the expression for acceleration, you got your dA dot, that is the derivative of this guy. Then you have your d theta double dot. Remember, the d dot's gone because that length, d does not change, so that one goes to 0. You got your d theta double dot, then plus dj theta dot. Now, what is that? J dot is going to be minus theta dot I. So that's minus d theta dot I. And they don't really show it until they get down here. And so where is it? So there's that guy. There's that one. There's the one I was just talking to you about, the minus d theta dot squared. This theta dot dA, ooh, that's the, okay, so I forgot to take the derivative of this. Okay, so when you take the derivative of this, you got to consider both the dA dot, which is here, and the derivative of the I. So dAI dot. Okay, what is I dot? I dot is equal to theta dot k cross I. That's going to be theta dot j. So theta dot j dA. So there it is. So does this, Stacy, what does this mean? Does this like help you at all?
I'm still a little lost. Okay, so we have the theta dot I and.
Let me see, do I have some more green paper? Because I could give you like an overriding thing to always do, and this will help. So whenever you take a derivative, you're always going to have, generally this is what you're going to have. You're going to have a vector. Let's say you have a vector r, okay? And that r is going to look like a r0 direction. I'm going to put the direction as, what's good for direction? Maybe we'll put E. I'll call it direction E. Okay, so this vector has this magnitude in this direction. Okay. Okay. So to take the derivative of that, then, so d, you know, it's got to be the derivative of r0 times e plus r0 Does that make sense so far? Because that's your basic product rule. Okay. Then, ooh, this looks weird on my thing, the way it's so, for you, it would be much better if it was not so tilted. So let's see here. Try to keep things a little bit straighter. Let's see. Okay. Okay. So then the next derivative. So then we should talk about what is this? Okay, so d dt of a direction, remember this is a unit vector, is going to be equal to theta dot, usually k, but it really is going to depend upon the problem. But if for these problems, it's a simple expression for angular velocity where it's just out of the page. So that's equal to theta dot k cross e. That's how you take the derivative of this little guy. So what you end up with then is dr. So what you end up with is r0 dot e plus ro theta dot k cross e. And k cross e, it would be much better if I made this a direction, because then I don't have.
Dr. Moore, it's a little off center. Like I can't see what you're writing now.
Okay. So let's see. So
okay, yeah, that's better.
So k cross e, we'll just have to, I really don't want to leave it like that. Let's say that k cross e is equal to theta dot e n. I'm just going to make it a new, and I hate to do that because a normal cross a, because this is really like, I'm using these i's and really, I mean these e's, and really it would make much more sense if there was a particular direction included. And I'm gonna go back and make that change. Even though you know it wouldn't necessarily always be an I, it might be something else. And then I, this is gonna be an I. And then it's theta dot k cross I is just theta dot j. So that makes that a little bit better. And then this becomes R0 I. This is what we call the transport theorem. R0 theta dot j. So now this is velocity. That's a velocity expression. Now the acceleration expression. So that would be dv dt would be the derivative of all this stuff. So you have r double dot o I plus theta dot k cross, oops. Now, in your problem, what you don't have here I'm going to go ahead and do like a similar situation, look up the top. So oh my gosh. Okay. So what we have here, oops, I was supposed to put this back here. Oh, I'm making little errors. Okay, so shoot, I'm so upset. Okay, let's see. Theta. Supposed to be a theta. Okay. So then, so we have something like this. So if in your problem, the difference is that you have some constants, like some length constants, that would need to be altered. But otherwise, it's a very similar situation. The difference is that I think you don't have, you have that term. D double dot, theta dot R dot, but you don't have this. Where did this, did I make a mistake? Where's my J's? Ooh, this is supposed to be R, okay. When I did this one, I left off the dot because this was R double dot and then it was R dot times that. So that means that here there was a dot and then there was a dot. Okay. Ooh, that means there's two of those. Yeah, there's two of these. So this is really, okay. So we went through taking these derivatives. We started with a vector that was rotating, right? So this I is a rotating direction, it's a changing direction. And we're allowing the magnitude to change also in this particular problem. So we have to take derivatives of both, but none of them become zero. This does not become zero. The I is also changing. So this is what we get for our velocity vector. One includes the change of the magnitude in the original piece, and one includes the change of the direction. Then we do the velocity. Notice, so we picked up an additional term because we had, this was derivative product rule. So then we get to here, we have product rule twice, well, three times, right? Because we have this one is a product and this is two products. So this is the derivative of the first, this is the derivative of the second. Then we come over here, we have derivative of the first, derivative of the second, derivative of the third, right? So 1, 2, 3 items. And again, we have to, when we take the derivative of the J, we got to remember that. How is the J changing? How is this direction changing? It's changing because of the theta dot. And so again, there's another theta dot K here crossed with that J. So really, it's almost like saying whenever you have, and I think the book may write it like, I don't know how they wrote that, but they basically said that if we take the derivative of a item that's a unit vector, we call it U. U, when you take the derivative of a vector U, and that's a unit vector, then what that's equal to is theta dot k cross u. That's how you take the derivative of a unit vector.
Okay.
So that will get you through like the acceleration stuff, and then you proceed. Anything else in here that's like confusing?
Yeah, I didn't see like why there's t/2 for part C. So for like
Oh, okay. Moment. A moment. So when you have a object that is rotating about some point, let's say, and you're concerned about saying, well, what is this moment going to be? There's some force here. Well, that moment is going to be equal to the force times the length, r. Now, in this situation, you have a force here and a force here. You're talking about the moment about some center point. I think you're talking about the moment. Oh, you're talking about the moment about G? Okay.
Mm-hmm.
G is a little further up. I think this is A back here. So the way you determine the moment is by the perpendicular distance r from the force. Okay. So what is that in this case? So here's one force going up this side. Here's another force going up this side. One is called FA. I think this one is called FD, and this is called FC, I think. And so what are those distances? The distance is, I think, the total length of this thing, we said it was page 386 or something. So T is the total distance. So what's the halfway distance? T over 2. So the radius is T over 2 to each case. This force is going to cause this thing to rotate about G this way, like it's going to cause it to rotate that way. So one moment you could say is FD times T over 2, because it's just like this was a force times a rotation point, right? It was a force times the distance to the rotation point. Here, the rotation point is G. So the distance to it, the perpendicular distance to it is T over 2. So that's one, oops, I put little d. It's FD times T over 2. What about the second moment? The second moment is created from FC, but it's going to cause this thing to rotate in the opposite direction. And that is going to be a negative rotation because it's clockwise, but it has the same distance, T over 2. So both moments together equals FD minus FC times T over 2.
Okay.
And K, because it's the moments are about an axis out of the page. That's where this comes from. I'm sorry, the K.
Okay, I see. Why doesn't FA give a moment?
Why doesn't FA give a moment?
Is it because it's perpendicular?
Well, the FA, I don't know why they put, I think it's probably part of some other problem. This force, FA, is perpendicular. Okay, like imagine like a car, okay, and there is a slight wind pushing against the car to this side.
Mm-hmm.
Generally, you will not consider that causing a moment about G because it's perfectly resisted by the friction forces at the wheels.
Okay.
Now, if this got to be very large, like you might be driving down the street and you have a very large side wind, it may actually cause your car to start drifting to the side or to start rotating, in which case you'd be afraid that's possible. But in this case, they're showing this force FA as being completely resisted, which is why I don't think they should really include this force in this particular figure, because it's of little consequence. I think it may be because some books will use one figure multiple times. And so maybe in some part of the book, they talk about this force causing some slight motion in this direction if it gets large enough, but not for this problem.
Okay.
Not the one we're looking at. Otherwise, you're right, it would cause, and you would have to look at it, it would be a negative moment, and it would be the moment, it would be a third moment, and it would be FA D minus.
Okay.
Yeah.
So like, I guess like why is it T over 2 and not like D? Like why are you
Always the perpendicular distance
okay.
to the force. And so in this problem, the perpendicular distance from G to FC, see, here's the distance. If you just say, what's the distance, is that. That's the distance from G to FC.
Mm-hmm.
But you only want the perpendicular component to it. The perpendicular component, this is the parallel piece. This is the perpendicular part. And that distance is T over 2.
Okay.
Yeah.
And then I started some of the homework, and I forget what number it was, but I was looking at like I know it's like figure 8.35, I think it is.
Mm-hmm.
The problem was like to use the Keynes equation with that for like 8.46.
Mm-hmm.
And again, like I was just like a little bit confused about like the moment of inertia part.
Mm-hmm. The moment of inertia. So
That just coming from like the disc and the pendulum, are those the two moments of inertia?
yeah, those are two moments of inertia that you're including. One is IO and one is IG. And those go and come into play in Keynes. So in this problem, I think it was also given as an IG term and will come into play with the angular momentum. So angular momentum is like an IG times the rotation rate.
Mm-hmm.
And the IG would come from the back of the book. So if you're doing a circle, so for a circle, the IG, the one going through the center, is equal to this 1/2 mr squared. And the H, since you need the HG for that disk, you would have IG times the rotation rate of that circle was given as, I think, that B dot. That's HG. And for the rod, you're using this one. And the IY is what you're looking for, right? Because that's one that goes through G. That's this guy. Times its rotation. And its rotation is represented by theta. Oops, by theta dot. So you would have HG for the rod would be equal to the 112 m L squared theta dot.
Okay. And then I just like add them like normal.
Add what?
The two different moments of inertia together.
Oh, okay. So what that gets into is, let's see, so you don't have an example of that. Each rigid body is done separately. So if you go back to like Keynes equations, that's where this N refers to. So this thing here is the number of rigid bodies you have. And the problem that you're asking me about now, you have two rigid bodies, you have a disc and a rod. So you do all of this for the like the disc, and then you add it to all of this for the rod. So they end up being added, but they're not, like, this is not the combination of a bunch of them. You do this whole thing for the disc as if the rod didn't exist. And then you do this for the rod as if the disc didn't exist, and you add those two.
Okay, that makes sense.
Yeah.
Yeah, that's all I've really like started with. Those are all the questions I had as of
Yeah,
now.
so remember in the notes, there is a problem that was a double mass connected by a bar. And what you'll see there, this was M, is that you'll see that the problem looks like it's 2 times done. Because you have like force, this probably didn't have any forces, but let's just say force minus MA plus H. Oh, you didn't have a moment here. That's probably why you're confused. M minus H dot. And that'll be for like the first mass. So let's call this mass 1. And you add that to the same information for mass, what's plus M minus H dot for the second mass. So you do it twice, and then you add the two together.
Okay. Okay, yeah.
And then you do this whole thing again for the next coordinate. Like if you have 2 coordinates, like in your problem, you have like a phi dot and a theta dot. So you do all of this for theta dot, and you do the same thing for phi dot, the whole thing again. So you have 2 pieces, one for each mass. And the difference becomes, the reason why these are not the same, why they don't equal the same thing, is because you got to remember in here, there are partials. Like you got to do a dot, right? So remember I'm showing parentheses plus parentheses, but to each one of those parentheses, you have to have the dot of this fraction, these partial derivatives. And these partial derivatives are with respect to theta dot, and then the next time you do it with respect to phi dot and with phi dot.
Okay.
So the inside, these guys don't change as you do for your first set of equations. Where did I write it down? So the inside parts, these things, the F minus MA and the M minus H dot, that doesn't change. What changes is what you're doing, the partials. You got these partials on the outside here. Those are with respect to theta dot the first time you do it. And the second time you do it, they're with respect to phi dot.
Okay. Okay. So the partials are what? So like the, okay. Because I just, like, I feel like, okay, we have like a position equation, and then we take the velocity, but like we write like everything. We're not just writing like the position for one part, because we're writing it like with regards.
No. You're writing it. You got to write as many position equations as you have masses.
Okay.
Because you need the acceleration if you have a multi-mass item, you need the acceleration of each mass.
Okay, so we're doing like all the parts of it are just separate, and then you just add it at the very end, but each mass is separate for each part of the equation.
Exactly. So again, look back at those notes for the 2 point masses connected by a bar. And what you'll see is that everything is done for mass 1, then everything is done for mass 2. And in that problem, there was also 2 generalized coordinates. It was a U1 and a U2. And you do everything for U1, which I think in that case was V, and everything for U2, which in that case was, I think, a theta dot. So you'll see both of those. What I did do is that was a new page of notes. It's like one of the last pages of notes in at chapter 8. I taught that, but I took that was not in your original notes package. I appended it to that PowerPoint. I recreated that PDF and I loaded it back up to Canvas. So when you look in the module for chapter 8, I think it's called something mechanics, analytical mechanics. If you look there, you will see the full set of notes. And at the end of that PDF, you will see what I'm talking about, where there's 2 masses, 2 generalized coordinates. So very similar to what you're doing, except it doesn't have, there was 0 forces and there were no moments in that problem. So you only are dealing with the M and the A. So if you look at like these equations, these guys went to 0 and this was 0. So all of this stuff is gone, but you still have these and you still have that. So you can still use these and you can kind of see how you do this twice. Once for the first mass, then for the second mass, and then you do the whole thing again for the next coordinate, which was theta.
Okay. Okay, that makes sense.
Yeah. All right, young lady.
Okay, thank you for your help.
You're welcome. I'm glad we were able to finally get together and get something done.
Yeah, honestly, I was like surprised that things have been as flawless with like starting classes and stuff. I thought that there would be more issues like that, like technical, getting in, getting out, things like that.
That must mean that we're better than we thought we were.
Yeah, I mean, like somehow like Dr. Clark like locked one of the students out of class one time. But other than that, I think if you like join late, the way he had it set that like if you came like in a minute late, you like weren't allowed to join anymore.
Oh my goodness. That was
So,
in robotic locomotion?
yeah. But other than that, there hasn't been any issues.
Excellent. Well, let me know if you have any other issues, okay?
Okay, thank you. Have a good weekend.
You too. Bye-bye.
Bye.